Hello, good morning.
Good morning, sir. How are you?
So, did you see the revised this thing I had sent?
Yes, I saw the correction. Now I think everything I had is clear.
No,
So yesterday,
it's not really a correction.
correct.
That's what I wanted to tell you, because the term explosion is used in this context. Only thing is you have to view it somewhat. So I will just tell you about it. See, explosion generally means that going off to infinity in finite time. Okay, that is how that thing started. But anything going out of the state space in finite time is also called explosion. Okay. So, for example, if you take a process which you want to confine only to, I mean, you will study it only till it remains, let's say, in the unit ball in Rn, okay, or in the interval -1 to 1 in real life. After that, if it goes out of that, you are not interested. So that kind of thing can also be called an explosion. Okay, that going out of the state space in finite time. So now coming to this context, if you consider the state space as just you exclude 0, 1, 2, 3, like that. Okay. So when the process gets absorbed, if 0 is an absorbing boundary, when it gets absorbed at 0, that at that time it has come out of the state space, namely 1, 2, 3, 4, etc. All positive integers. Okay. So viewed in that perspective, such a thing called explosion. And in certain contexts, it is also of interest to extend the process beyond explosion. That is, even if explosion, as in the conventional sense, it is going off to infinity in finite time. After that, you can throw the process back into the state space with a certain probability measure, which will act like an initial distribution. And after that, it will evolve. Maybe again, the explosion might be repeated and so on. Or in some cases, what are called killed processes. Killed process is something like absorption, but then at the boundary happens to be, let's say, a set in Rn. You may not be interested in the probability of absorption. After that, you may not be interested. So in that case, to sort of the theory is reasonably uniform, you designate some state which is outside the state space, supposing the state space is the unit ball in Rn. If it goes out of that, you design some state outside of that. Need not even be an integer. It can just be an arbitrary symbol and call it the symmetry. So it is killed. So after that, it is in the symmetry. So such things, the difference between a killed process and absorbed process is that the killed process, you really don't care about what happens after it goes out of that domain. Whereas absorbed things, if the boundary is an interesting thing, suppose at the boundary it takes a particular value and so on, then in that case the absorbed process will be of interest. Say, for example, this you may not see in this course. There are connections between Brownian motion and partial differential equation. So partial differential equations, there is something called a Dirichlet problem. So that is, given the boundary value, determine the solution. So for such cases, the absorbed process would be useful, because for such solutions, one can give certain representation in terms of the Brownian motion and so on. So anyway, but certainly in our context, since we have been taking the state space as 0, 1, 2, etc., I think that confusion is better cleared. So I had avoided the word explosion in the revised thing and given explicitly what is meant by that condition. That is, the tau n's are all finite and the limit goes to infinity. Okay.
Thank you.
So now we will go to today's thing. Yeah. so we will now look at what is called the Brownian motion. Together with the Poisson process, Brownian motion is the most important among the stochastic processes. Brownian motion and Poisson process. So we have already seen Poisson process. So now we will look at the Brownian motion. It is mathematically more complicated. And okay, first of all, what is the Brownian motion? It is historically, well, Brownian motion, okay, when I go to the next slide, I will tell you more about it. So this is the first process which was thoroughly studied and extensive mathematical development. So a lot of big names are associated with it. And not only that, the study of Brownian motion also had a lot of influence in the development of probability theory as a mathematical discipline. You might have seen some places that till 1900 or even a little later, there was a debate whether probability should be considered part of mathematics or physics. And of course, now people say that some people say it is part of statistics. Well, as it is, probability theory, I would consider is a mathematical discipline, which has taken it has been influenced by developments in statistics, and it provides certain kind of mathematical basis for the subject of statistics. Because as in mathematics, in probability theory also, the way you derive things depends on deductive logic. Whereas statistics, especially the applications of statistics, what is involved is inductive logic. Anyway, let us not consider those things. And also probability theory has a lot of connections from physics that has been clear even from early days. And of late in economics, of course, engineering, especially electrical engineering. As a matter of fact, many electrical engineering departments have a very, very highly developed courses in probability and stochastic processes, including in India, many of the IITs, IIT Bombay, for example. And yeah, so the study of Brownian motion has also had a deep influence on the development of probability as a mathematical discipline. It has many surprising esoteric properties, which some things I will mention, but unfortunately we will not be able to prove because we are not going to look at the rigorous derivation of Brownian motion, etc., etc. So, but anyway, I will mention it later. And also, of course, it is a very versatile and useful mathematical model, and or as approximation in various applications. Unlike the Poisson process, Brownian motions models can be considered basically only as approximations. Whereas Poisson process it actually describes the processes in certain situations under certain conditions, of course. Yeah. However, theoretically, this is a very rich subject. But you may note it down if you want to. Okay. So physical phenomenon of Brownian motion was discovered by botanist Robert Brown about 200 years back. So you might have studied or come across this in your statistical physics courses or physical chemistry courses, etc. So this is the way Mr. Brown observed it was when pollen grains, pollen dust of certain flowers were, let's say, they land in water, suspended in water. So they seem to be moving aimlessly, incessantly, and it is without stop. Apparently, what I have read somewhere is that he kept a beaker containing water and also pollen dust for about 2 or 3 years in one's place without disturbing it. After even 3 years or something, he found that motion was still as robust as it was on day one. So he had this thing to realize that it is something which is fundamental property of particles of that size. So the size also in some books you might have mentioned it, and these are also found in certain colloidal solutions of liquids, and more importantly, colloidal solutions of gases, what are called a dilute gas. Dilute gas is generally the name given by physicists for those gas medium, that is mixture of gases, where Boyle's law is obeyed fairly strictly. The closeness with which the Boyle's law is obeyed in this thing more or less determines the dilute gas. So however, a mathematical description of the phenomenon was first developed by Albert Einstein in 1905. 1905, you might have read, Einstein published 3 great papers. One of the papers concerns Brownian motion. So he tried to give a description from the laws of physics. And Einstein realized that the study of Brownian motion, say even in around this time, 1905, though the atomic theory of matter has been propounded by John Dalton about 100 years before that, there was really no experimental proof of this fact that the atoms exist. So his idea was that Brownian motion process can be used to show that atoms and molecules do exist. And of course, from Einstein's study and using various sophisticated ways of measuring and so on, I think a Frenchman, forget his name, Perrin, he actually showed that performed an experiment about in the 1920s to show that atoms do exist using Brownian motion, for which he got a Nobel Prize in physics, I think in 1920s. And there are further developments, mathematical developments, due to Smolchowski, Fokker, Planck, Berger, Ornstein, Uhlenbeck, and of course, S. Chandrasekhar, all these people in the early part of the 20th century. Yeah, you can note it down if you want to. Mathematical formulation was first given by Norbert Wiener in 1918. And important later work by Kolmogorov, Feller, the same Feller as who has written the famous books, 2-volume book, William Feller, Kolmogorov, and most notably by Paul Levy. Paul Levy is considered as, it seems, all the trajectories of Brownian motion are his friends. I mean, that is a popular way of showing that he has done some intricate these things concerning Brownian motion. And maybe more interesting for younger people, a heuristic formulation and many interesting properties were obtained by the Frenchman Louis Bachellier from a study of fluctuations in stock prices in the Paris stock market in 1900. That is 5 years before Einstein. Einstein 1905. Bachellier 1900. It was not very mathematical, but heuristic, quite many of the ideas. I think he was supposed to be a student of Henri Poincaré. So as we were mentioning concerning the pollen grains, particles undergoing Brownian motion exhibit kind of ceaseless, that is, it doesn't stop, irregular motions. There is no regularity, or you cannot see any kind of regular pattern. So it is not a periodic or any such thing. So it seems to be haphazard. You cannot really predict at the next moment where it would go to, which part of the this thing vessel it will go to. That is in the liquid medium. So such a phenomenon happens when there will be a medium consisting of two types of particles. We will call them solvent particles and solute particles. So solvent particles are, say, that is in analogy with that pollen grains in water. Water, it is analog of water, solvent particles. Solute particles is analog of the pollen dust. So this happens when solute particles of a certain size. That is, the size of the solute particle should be considerably bigger than the solvent particles. But the solvent particles numerically are much larger. So if you refer to some books which deal with colloids, they may give you exactly in which range this kind of a thing happens. I think between certain millimicron to certain millimicron, that should be the size of the solute particles. So colloidal solutions need not be liquid, it can even be gaseous solution, one gas in another gas. Or that is dilute ideal gas. Dilute ideal gas is what we call if that gas medium obeys the Boyle's law fairly well. By the way, though we call it solute and solvent, in this case, the solute particles are not going to dissolve in the solvent particles. I mean, this is just a terminology. Basically meaning that the solute particles are much larger than these solvent particles. Solvent particles are much smaller compared to the solute particles. But however, numerically, they are much larger. So this kind of description you keep in mind, because something what we are going to say later also comes into that you can immediately tie up. Oh, by the way, what we are trying to drive at is we have to arrive at a reasonable definition of Brownian motion. In Poisson process, we stated the postulates, which are all quite natural or reasonable postulates, and from that we could easily derive. Here, that is not the case. So we have to get hold of the solution, and then afterwards we'll assume that objects satisfying these requirements do exist, which you will call Brownian motion process. Okay. So this solute particle is usually called, in that such a situation, is the Brownian particle. So this motion is purely due to when that Brownian particle is constantly kicked around by a very large number of but much smaller solvent particles. So all the particles are in constant motion, especially the solvent particles. And because of their motion, they collide with the Brownian particle, and that causes the Brownian particle to move. Just one or two particles hit the Brownian particle is not going to budge. So this is the motion caused by the particle, the solute particle or the Brownian particle being constantly kicked around by a very large number but much smaller solvent particle. So it's also assumed that there are no external forces acting on the system, or when effects of such forces are negligible. That is negligible in the sense that in that Brownian motion, that pollen grain and water, the effect of gravity was negligible in such a situation. The particles are much too small. So the effect of such external forces can be considered negligible in that context. So this motion is purely due to the fluctuations of this particle caused by this constant bombardment, like a football being kicked around. Yeah. So Brownian motion is purely motion caused by fluctuations which the solute particle experiences due to the innumerable collisions with the solvent particles. And among these, the solute particle is suspended. Okay, you take down if you want to. Yeah, it is also assumed that the solute particles do not interact among themselves. In particular, there are no collisions among the solute particles. So between one solute particle and another solute particle, there is considerable distance. So that is why the dilute gas. So no interaction among these solute particles. Interaction at the basic level is collisions. As we mentioned earlier, the solute particle does not dissolve in the solvent. And also there is no chemical affinity between the solute and solvent. No chemical reaction. So it's purely a physical phenomenon. Yeah. So because of all that description, we can consider this thing as a motion of a tagged or marked solute particle. Let's say we pick up one particle solute particle, and track its movement. So that might be considered as a typical trajectory of a Brownian particle when that solute particle is in a solvent medium. So the solvent medium will be assumed to be uniform. So there is no concentration gradient in the solvent. Same concentration everywhere. Because if the concentration happens to vary, then the denser things will have more attraction. No temperature difference throughout the medium. So the entire system is kept at a constant temperature. So in physics, this kind of a thing is called homogeneous isotropic medium. Isotropic means same temperature, and homogeneous because the same concentration. No external forces are acting, and no temperature or concentration gradient in the system. That is, at one end of the system is at a higher temperature than the other, or at a higher concentration than the other. Let's say these are all these things of part of this homogeneous isotropic medium. So now to keep the discussion simple, of course, if you are considering a realistic real life model, it has to be three-dimensional model. We will consider only the one-dimensional situation. So you can view it as a one-dimensional projection of a three-dimensional. So this is to sort of give you a kind of feel for what is happening. So we will now go for a heuristic discussion. Heuristic means some sort of intuitive. Nothing is going to be proved here. Our objective is to arrive at an appropriate definition. So because of what we discussed earlier and certain other observations, we consider how to put it in the framework of probability. So let omega AP denote the probability space, and BT, let us say, denote the one-dimensional Brownian motion, continuous time. So what are the salient aspects if you adopt this kind of a situation? So B0 is 0. Let us say the particle starts at 0. And this is a BT is a real valued random variable. We are considering the one-dimensional situation, real valued random variable on the basic problem. Random variable basically means in this context that the exact location of the particle cannot be determined at any positive time. At best, you can hope to make with what kind of probability the particle may be in a region at a certain time. The exact location of the tagged particle you cannot determine accurately. Of course, as by a stochastic process, we know that there are two variables. One is this time variable, another is the random omega, which comes from this guy, capital omega. So for any fixed omega, as a function of t, it is a continuous function. Of course, that is because that is a physical requirement. The movement of the particle should follow a continuous path. And this is a pretty obvious requirement. And this is very crucial. Okay. Now we put certain probabilistic assumptions, namely basically independent increment property. Let's say T1, T2, T3, T4, they are in ascending order time points. Then note that T1 to T2 and T3 to T4, they are disjoint time intervals. So B at T2 minus B at T1 is the net displacement of the particle in the interval T1 to T2. The guy is at the BT1 at time T1, and then later on it is found in, let's say, BT2. So this minus that is a net displacement. We don't know anything about what happened in between, except that that should have followed a continuous path. And in a similar fashion, BT4 minus BT3 is the net displacement of the particle in the interval T3 to T4. So what this means is that knowing one of this net displacement does not give you any knowledge about what happened during the other displacement. So knowing one of them does not help in any way in knowing the other thing. So to translate this into probabilistic language, thus these displacements in disjoint time intervals are independent random. So that's what we are saying here. These are independent random. Of course, this requirement can be extended to n disjoint time intervals. So if you have T1, T2, T3, T4, T5, T6, etc., n of them. That similarly, n you can get hold of n independent random variables. And that is one way of saying that the independent increment property holds, which we have seen in the Poisson process. Okay. So where does that lead us to? Okay, so fix a t. So for any integer greater than or equal to 2, you divide this interval 0 to t into n equal subintervals, each of length t over n. And note that one can write bt equal to bt minus b0 because b0 is 0. So you can write this bt minus b0 as the sum of this n guys. You can easily check. And 0 to t over n is that, and 1 over t over n to 2t over n, etc. These are all disjoint intervals. So the summands here, they are all net displacement of the Brownian particle in disjoint intervals. So by our earlier assumption, this is sum of n independent random variables. Now keep in mind that this is a heuristic discussion. Yeah. So Bt can be written as a sum of n independent random variables for every n. And as the trajectories of the path, process are continuous paths, and in view of our knowledge of central limit theorem, perhaps one can conclude that each Bt has a normal distribution. Continuity is important. Note that Poisson process also, that Nt can be written as a sum of n independent random variables. Okay. So there you don't have the continuity of sample paths. Here you have continuity of sample paths. And there, of course, with that we actually derived the Poisson distribution, Poisson process. So keep that in mind. So that is why it is only a heuristic discussion. So continuity plays an important role here. You don't expect any trouble in going to the limit, etc. So because of this, we can postulate, okay, it's not a proof, it gives some idea that probably BT has a normal distribution for every T.
So here are we assuming that BT is normal or
No, we are
speculating that PT will be normal?
No. We are neither assuming nor deriving anything. The objective is to get hold of a definition, okay, of Brownian motion. See here, unlike the Poisson case, we cannot prove anything at this stage. Okay, we are groping in the dark. What should be the definition? If you have a definition, you can work towards a definition and derive certain properties and things like that. And later on, one can try to prove certain things. Okay, that is why here the discussion is completely heuristic or intuitive. So this is our hope. Okay, that namely saying that BT has a normal distribution and also it has this independent increment property and so on, and then continuous sample paths and things like that. We hope that it will give us a good object, okay, useful object. The usefulness of the object will have to be, that is, it has to prove itself later. We are taking the risk of saying that BT would be normal, okay? This is not a proof. That's why it is not a rigorous argument. We have to arrive at a definition of what this guy has to be. Which definition meaning it has to be stated in a precise mathematical terms. I mean, in mathematical things, you define something, but then sometimes you can question that why is that definition? I mean, what made somebody to come across or put forth that kind of a definition? So here we are trying to answer that kind of a curiosity question. For example, when you studied the set theory at the beginning in any mathematical course nowadays in BSc and various things, something is defined as a set. Why the hell should you have set theory and so on? Well, set theory is the kind of ultimate this thing of, let's say, Cantor's research, which started, it has its origins in the analysis of Fourier series. The places where Fourier series can converge or diverge and things like that. So that led to, I mean, the places where certain things don't diverge or don't converge, or it may converge and may not represent the function and things like that. Those are questions which Cantor and some of his contemporaries were wrestling with. And ultimately, this thing was, they found a good, this thing called set theory. Incidentally, set theory was not easily accepted by the mathematicians of those days. Almost till the end of Cantor's life, it was not accepted, really. Now we are introducing even in schools and things like that, which is, I think, is not correct. It is not just a set consisting of set of brothers, sisters, and things like that. It's not. That's all just okay. Yeah, good way of introducing in lower classes. If somebody asks, why the hell should I study this? The teacher will have no answer really. Whereas many other things in school, mathematics, addition, division, multiplication, those things, anybody can explain why that are useful. Same thing with measure theory. If that, if right in the beginning, a measure theory is started, everybody will question, why the hell should I study it? So measure theory is something which will sort of make things in analysis, probability, etc. clear and can be made rigorous. That is why it is introduced later, after studying a bit of analysis and a bit of probability and so on. Any subject you can ask the question, no, why should I study it? What is special or why is this being imposed on me? I mean, don't you think that those are natural questions any student can ask? Of course, one reason you can say it is in the syllabus, and to get your degree, you have to study it, okay? All right. So one may postulate. So we are going to say that in our definition that BT has a normal distribution for each T. And since, as you know, normal distribution is determined by two parameters, let us say mean and variance, we may include them also in the definition. We are going to call something as standard Brownian motion in the next class. Yeah. So first, look at the mean. D0 is 0. And the solvent medium is assumed to be homogeneous. So at any time, there is equal probability of the particle being on the positive side or on the negative side. And this sort of indicates or suggests that one may take the expectation of BT to be 0 for every T. Next, variance. We know variance is a measure of dispersion above the mean from our knowledge of probability, statistics, etc. And as time progresses, the particle may tend to go here and there, wander further away from the mean. So variance is a measure of the dispersion. So therefore, variance of BT will be an increasing function of T. Variance is always positive, right? Non-negative. So any increasing function you can, in principle, take, but we have to standardize certain things. So one may take variance of BT to be T itself. It's an increasing function of T. That's T varies over positive. Right. The process has independent increments, and in our discussion, the time homogeneity seems implicit. So another thing, simplification for the standard, what is going to be standard Brownian motion, we can take that BT plus S minus BS can be taken to have the same distribution as BT minus B0, which is BT. Time homogeneity in the process. Or stationary increments. Stationary independent increments. So it has certain similarity with Poisson process, stationary, the homogeneous Poisson process. But the main difference that is very, very, very crucial is that here the sample paths are continuous and there the sample paths have jumps. So one can define the standard one-dimensional bond. We are using the word standard because we are going to take the mean as 0, mean as 0, and variance as this. Therefore, BT will be a normal, it will have a normal distribution with mean 0 and variance T. So that way it is standardized. Non-standard means you can take, first of all, there can be a drift. So expectation of BT need not be 0. It can be a constant times T or something like that. And similarly, variance can be an increasing function. And so on. Generally strictly increasing. Because if variance is going to be a non-decreasing function, then there will be complication. I mean, and that means in a certain region, it is frozen. And so on. So one may formally define the standard one-dimensional Brownian motion as follows, and that as follows will be the next class. So today's thing, what we have done basically is that we have given certain heuristic or possible things so that we arrive at a reasonable definition. And once we give the definition, we will assume that a stochastic process satisfying those assumptions exists. Because to prove that that exists, one has to develop a lot of tools. Basically, tools like we have to do bit of measure theory on spaces. Let's say this sample paths are here continuous, no? Therefore, on the space C01 or C0 infinity, that is, the C0 infinity stands for the collection of all functions on 0 to infinity, which are continuous, real valued functions, which are continuous. Or C01, if you go consider up to time point 1, all continuous functions on continuous real valued functions on 0, 1. So that is a metric space, complete separable metric space, and you consider probability measures on that. That also can be considered as a measure space, metric space. You can define a metric on that. All those kind of tools you will need to even to prove that what we call a standard one-dimensional Brownian motion exists in the mathematical sense. Just like we used to say, let X be a random variable having a standard normal distribution. In earlier probability stat courses, one assumes that such an object exists, such that probability X taking value in some interval AB is integral from A to B, that integrate that Gaussian density. But to prove that such a thing exists actually, you have to exhibit a probability space, a function or which can be called a random variable, such that it has the given properties. And similarly, here if you want to do that, you have to exhibit some probability space and a collection of random variables, which is a stochastic process, which has these properties, which we are going to define in the definition of standard Brownian. And those mathematical things are beyond the scope of this course. So we will define this object, assume that such an object exists, and then look at some of its interesting properties which are accessible with our level of knowledge now. Okay. So there is always this thing that the develop, or you want to do things very strictly mathematically and in a sequence, then you have to go through all these things first. That is the doing the measure theory on C01 spaces, that function spaces like C01 and so on, and then come to this. From a pedagogical point of view, it is better to sort of sidestep that kind of requirements in the beginning. So what here we have done is that all the heuristic arguments is to arrive at a reasonable definition of this guy. So now, assuming that this object exists, we will see there are certain properties which are interesting. So that some of you might consider it worthwhile to pursue things like measure theory on such function spaces and things like that. All the mathematical details, you are also have to do it first and then see these things that might drive away a lot of people. It's not healthy also. And even subject didn't develop like that. Only after it was realized that Brownian motion is an important object and things like that, then only they started looking at how to define it mathematically, leading to many development of many tools for probability theory. So we will stop here for today. So if you have any questions or you want me to go back to any of the slides, I'll be happy to do that.
One thing, could you just go back to the mean slide, the expectation of B of T?
Pardon?
The expectation of B of T. Could you just go back there once?
Yeah.
Okay, great. Thank you. That's
So the heuristic argument is this.
yes, I got it. Just need to see if
And
I read it.
similarly for variance.
Okay. And could you suggest a reference?
Pardon?
Could you suggest a reference for this Brownian motion?
Reference, see many of these, say for example, Carlin and Taylor. But again, Carlin and Taylor doesn't give a proof that standard one-dimensional Brownian motion exists. It is beyond the scope of even that book. Okay. So for that, you have to take up, say for example, Billingsley's book might give. Billingsley's convergence of convergence of probability, convergence of measure, or measure, that not the probability and measure book. There is another book, convergence of probability measures or something like that. Okay, that's a smaller book, but it is more specialized. And then there is also a book by the Bhattacharya and Wemeyer, Stochastic Process and Applications. But those are all advanced books. Then Doob's book and KRP's book, Probability Measures on Metric Spaces, not the probability measure book. I think Karatzas and Shrev, Brownian motion and stochastic integrals or stochastic calculus, that also, I think it gives, though it concentrates on stochastic integrals. So books like that. Advanced textbooks, and many advanced textbooks on stochastic process, which also include the measure theoretic these things. paraphernalia. Gehman and Skorohod. Many of these books are in CMI library.
Yeah, I remember seeing the names. Yes.
Yeah. The Billingsley's book is a standard reference. You can also look at the other books. I mean, you go to the stochastic process section and pick up a book at random. There is a good chance. I mean, especially the more advanced books will give you this. There are also some later books. Yeah. But those books, please, they're not for this course.
Yeah.
I mean, this Sheldon Ross, Hoyle Pottenstone, they also discuss things about Brownian motion at assuming that the Brownian motion process exists. That an important elementary calculations and things like that. So even though some of these things may be even at the higher undergraduate or MSc levels, these are just basically to whet your appetite. Okay, anything else? Otherwise, we can stop for the day. Okay.
Thank you, sir. Have a nice day.
So you too. Thanks a lot and see you on Friday.